along with Erhard Serikat. Indeed, this use case that I'm going to talk about is a real use case proposed by a Spanish company, Air Transit. This is a logistic and transportation company. It has a lot of operational hubs in Spain, in big cities such as Barcelona, Bilbao, Madrid, Valencia. There are big cities, and also, and this is going to be very important for the use case, also in the Balearic and in the Canary Islands. Also, I want to say that this use case that I'm going to talk about is part of a Basque-funded research project, which is called Q4Real, which objective is to bring quantum computing to the industry, just to make some proof of concepts and some pilots. We were, because the project has already finished, we were a consortium with partners such as Multiverse, Mercedes-Benz, the University of the Basque Country, and also Tecnalia and Erhard Serikat, which are the ones that work in this use case. Also, let me one slide to say that within this project, Q4Real, we work in another use case, another industrial-related use case focused in the three-dimensional beam packing problem. If you want more information, here is the paper. And why I am talking about this use case, because I already talked the last year about this use case in another webinar with DWave. So if you want more information, you can also see the webinar that we provide jointly with DWave and Tecnalia the last year. And now, yes, I'm going to talk about the problem that will be the focus of this webinar, the logistic problem, the routing problem that has been proposed by Air Transit. The main objective is so simple, is so common in the logistic industry, is to optimize the cost of delivering a set of orders using a fleet of trucks. We have some characteristics and some restrictions, and the solution that our system provides should determine which trucks must be used within the fleet, which are the routes that these trucks must follow, and what are the goods that should be loaded in each of the trucks. There are some restrictions also that we have to take into account. In this presentation, I will focus in four of them. The thing is that the capacity of each truck and the capacity or the characteristics of each package is measured using two aspects, the width and the dimension of the packages and the trucks. Also, a single client could have more than one delivery, and these deliveries can be served in different routes. This is something that is different from another more academic problems, such as the vehicle routing problem. Also, there are some clients that can have a priority. We call these clients priority deliveries. These deliveries which must be completed before a certain specific time. And lastly, the drivers must not work more than his working hours. For example, if we calculate 3-4 different routes, so we need to take into account that one single driver can deal with several routes, but he has never or she has never drive more than his working hours. So when we when we thought how we are going to address this problem, when Air Transit talked about their use case, we thought about how we are going to deal with this problem. The formulation could be, it sounds familiar. So the first idea was to deal with it using the classical TSP or Trebling-Sussman problem or vehicle routing problem formulations. Indeed, as we already conclude in our systematic literature review that we published some years ago, almost or many of the papers that we can find in the literature focus in routing problems and quantum computing, they are focused or they embrace the Trebling-Sussman problem or the vehicle routing problem formulation. And this is something that it is still actual in the literature. Many of the routine papers, they adapt the use case to the vehicle routine problem formulation or traveling salesman problem formulation. And this is good. We have, and today we also work with using the traveling salesman problem and the vehicle routine problem. But the main issue working with these formulations, it is that at the end of the day, they are academic problems. So it is very difficult to find a variant of the vehicle routine problem or a variant of the traveling salesman problem that really adapts to the real needs of a real logistic company. And our mission with this solver, with solving this use case, our mission is to solve the most real problem. So what we think at our first thought is to build an iterative algorithm which will be calculating the routes and the subroutes little by little. And we thought about which is the most restrictive constraint of our problem. And we thought that this restriction is the priority deliveries. If we don't meet this restriction, all the solutions will be unfeasible. So we thought that our main objective is to visit as much clients as possible prior the visit of the most priority delivery. For example, in this very small example, we have a warehouse and we have a set of clients. In this set of clients, we have a priority delivery, which should be served before 70 minutes after the starting of the working day. But the thing is that the traveling from the warehouse to this delivery, to this priority delivery, it is just 30 minutes. So what we thought is, okay, so we are going to build a mathematical formulation that prioritize to visit as much clients as possible prior the visit of the most priority delivery. So we first build or calculate a first subroute, and then after we calculate this subroute, then we can calculate another subroute to go back to the depot with all the deliveries or as much deliveries as possible served. So how we solve this problem, how we solve the routing problems or the routing sub-problems that we are going to deal in this use case. Okay, for doing that, we use the CQM, the constraint quadratic problem, the constraint quadratic model hybrid solver of DWave. Because with this solver, we can very flexible way, we can design and define the constraints of our problem and also the variables and the objective function of our problem. So this is the main workflow of our solver. It is an iterative solver, as I said, in which the subroutes and the routes are being calculated until all the clients are served. And I'm not going to go through the mathematical formulation in this presentation. We have a paper published. We have a couple of papers published. I'm going to share the links at the end of this presentation. You can drop me a mail and we talk about the papers. So I'm not going to go to the mathematical formulation because it is very dense. If you want it, you can go to the paper, but I'm going to talk about aspects that allow us to solve the problem and also some mechanisms that we have developed in order to solve complex instances, okay? The first thing that we need to know is that our solver, using the same mathematical formulation, it can solve 3 different of subroutes or routes depending on the needs or depending on the characteristics of the remaining clients to be attended. So we have the to priority subroute, we have also the to depot subroute and the no priority route. So This is a brief example, this one. We have a 14 delivery instance in the left-hand side of this slide. So we have just one priority delivery circled in red in this slide. And first, what our system make is to ask if we have a priority delivery. Yes, we have it. So first, we calculate a two priority subroute, which starts from the depot and finishes in the location of the most priority delivery. Then, when this subroute is calculated, we need to calculate a to depot subroute, which departs from the location of the most priority delivery and which should end in the depot. Then, when we calculate the to priority and to depot subroutes, they are merged to build a complete route. And in this case, because we don't have more priority clients, so in this case, we build a no priority route. We calculate a no priority route, which in this case serves all the remaining demands. So the objective function of our routing problem that I said, this objective function and this formulation is the same for calculating the three types of routes of the system. So the objective function is a B-objective one. It is not a multi-objective problem. It is a B-objective problem in which we have two different objectives that are weighted. There are weighted objectives. The first one is to maximize the number of packages delivered prior the visit of the most restrictive client or the depot, and also minimize the total cost of the route. So here, this is an exception. What happens if there are no priority deliveries? Okay, in this case, the algorithm tries to build a route that maximizes the number of deliveries, minimizing the cost of the solution and not surpassing the capacity of the track and nor the remaining working hours of the driver. So now I'm going to talk about a very interesting instance reduction mechanism that we built for our solver, because I guess that in the audience, there's researchers, practitioners, people that work with logistic problems. Logistic problems, despite it seems a simple problems because the formulation is simple, they are very complex problems to be calculated, to be solved by quantum technologies, quantum computers, because there are some restrictions and the complexity scales very with very small number of clients, of very small visiting points. The complexity scales a lot. So I'm going to talk about one classical preprocessing, well, in this case, is a preprocessing mechanisms that we use to reduce the complexity of a two-priority routing problem. So in this case, imagine that we have one priority client that we must to visit before a certain hour, and we need to depart from the depot. So we calculate which is the distance or the cost from going to the depot to this priority client, and we assume that it is not so efficient to go further from the most priority delivery, to go further prior going to visit this client. So we calculate like a circle using this distance, this cost as a radius of the circle plus a little offset of distance, and then we make the inverse process with the cost between the the most priority client and the depot, and all the nodes that are placed in the intersection of these circles. These nodes are going to be part of the sub-instance that we are going to solve. It is so important that to note that not all these clients must be visited in this sub-instance. So we calculate the two priority route using these smaller instances. So this calculate is going to be more efficient. Then we calculate the to the pod root, in this case with no preprocessing mechanisms. We merge the roots and we calculate the remaining root using a no priority root. So this is one of the mechanisms that we have developed for making our system more efficient. I'm going to talk now about another instance, another kind of problem, another kind of use case that we can find in the real world. In this case, we have two different priority clients that cannot be served in the same route. And also, we have one client that has two deliveries that we are not obligated to visit it in the same, with the same route or with the same track. So in this case, first we calculate a two priority route to visit the first most priority delivery. And then because we cannot visit the other most priority client, we just calculate a to the pod route. We complete the complete route. Yes, we build the complete route, merging these subroutes. And for attending the other priority client, we build another two subroutes. And here, with these solutions, one could think, okay, why, if there's one client that has two different deliveries, why we are visiting it using two routes? Why not to just provide all the deliveries in the same visit? So for doing this, for this kind of situations, we have developed another mechanism. In this case is the friendly routes. In this case, it is a classical post-processing mechanism used to refine the routes in order to make them more driver friendly. For example, in this case, we see that in the purple route, we visit the 14 node, and in the blue route, we don't visit it, but we go through very, very near to this client. So what the system does is to analyze the remaining capacity of the blue track, or the track that is going to develop or is going to perform the blue route, and it checks if there's remaining space in the track to serve this 14 client. If it is possible, so the routes are recalculated to make them more driver friendly. Now, I'm going to talk about a very interesting also another instance reduction mechanism, in this case for solving no priority routes. So imagine that we have this instance in which we don't have priority clients. Again, for the people working with quantum computing, logistic-related problems, this is quite complicated problem, even if you work with a CQM RealWorld solver. So when we thought about how we can deal with these big problems, the first thing that we thought is, okay, we are going to use classical artificial intelligence optimization or clustering algorithms. For example, a genetic algorithm. We have the experience, we can develop it, and we can do it. But solving this kind or using this kind of algorithms could be no efficient. So, for example, imagine that we develop a genetic algorithm, we execute it, and the result is these three clusters. Okay, we can see that the blue cluster is so big. So what happens if we build a route, but not all the deliveries in this cluster are served by a single track? So in this case, we need to recompute again the classical genetic algorithm, and this is going to be very, it is not going to be very time efficient. So we can think also that, okay, so this is another alternative. So build smaller clusters, and each cluster be served by one track or one route. But this is also a non-efficient solution, because if the clusters are so small, maybe we are going to left a lot of remaining space in the track. So what we think is, okay, we need a very fast mechanism, a very fast algorithm, a very fast technique, and it should be adaptive, okay? So we thought to make a very simple mechanism that it does not take a lot of time. What we make is first to check which are the farthest nodes in the instance, okay? The farthest clients. We can assume that these two clients are not going to be served in the same route. So in this case, we choose one of these clients, and also taking into account the distance between the depot and this client, and adding a surplus of cost or distance, we build a sub-instance, a sub-problem, or the whole scenario, and then we calculate the route using this sub-instance, okay? We calculate this route. As you can see, not all the clients, not all the demands are served in this route, and then we make again the same process. As I said, it's a simple process, but it is very fast. The thing is that in our solver, if we need to solve 5 different routes, we need to call to the DWave CQN hybrid solver 5 times. So the rest of the algorithm should be very time efficient to solve the problem as fastest as possible. So in this case, again, we repeat the process and we build the other route. And in this case, we can solve this kind of big problems. So let me say that, let me show you a demo, okay? I'm going to show you a demo. This is the main code that we prepare. I'm going to run one instance with 2 different priority clients and 22 clients. So I'm going to run it. And here, this is going to appear a folder about the instance that we are going to solve is going to be created. And in this folder, all the information of the instance and the solution is going to be inserted. So here we can see there's one subfigure folder and the graph. This is the graph. This is the graph of the problem that we are solving. And here in the subfigures folder, they are going to be put all the subroutes that will be calculated. This is one of the subroutes, and the other subroutes will be calculated. Here, if you can see the prompt of the console of the PyCharm, here you can see that the system sets, okay, the track cannot reach the next highest priority node. Why? I say that we have 2 priority nodes, but we cannot visit them in the same route. So the system proves it, the system checks it, and calculate the routes, taking into account this kind of situations. So the routes are being calculated, the subroutes are being inserted in the subfigures folder, and when all the routes, when the execution is ended, so in this moment, all the complete routes are created in the folder. In this case, we also created a info data frame file with all the information about each subroute, each complete route, with all the total cost, the total weight, and the total dimension of the solutions. We can run another instance, in this case, a bigger one with no priorities. But before we can see, before seeing the solutions, I want just to check. This is just you to see that what you have seen now is a real execution in the real hardware of DWave, because here you can see the access use is more or less 7 and 5%. So if we updated the account, we can see that this amount has been already increased, and you can see that all the executions with the time right now have been executed. This is just to see, just to demonstrate you that the demo that I have shown right now is a real demo, and all the results that I am demonstrating are real results. Okay. So here it is a bigger instance. We have 28 clients to be visited. This is the whole instance. In this instance, this clustering that I have talked about this very fast mechanism is being calculated just to try to build the most efficient routes. So I think that there are 4 routes that are being calculated. In this case, there's another interesting thing to see is that the truck has not consumed all its working hours, but it's time to take another vehicle. So in this case, there's the friendly routes mechanism that I talk about, just to make the routes friendly for the drivers. And this is the routes that we have already, calculated. In this case, if we open the file, we can see that 3 of the routes are performed by the same track with the ID 0 track, and the other one by the track with the ID 1. This is just to respect this working hour restriction that I talk about. And now let's go to the final part of this presentation, because I'm going to talk about the real world proof of concept that Erhard Serikat and Tecnalia have developed with Air Transit. The main objective, the real objective of this use case, in this case, is to optimize the cost of delivering a set of 44 orders arriving at Air Transit Depot in Palma de Mallorca, in Spain, and the deliveries should be scheduled once the packages have arrived at the depot from the port. We have different restrictions, different characteristics, and in this case, there are 2 characteristics that are quite interesting. The 2 last ones, the travel times are calculated using real routing distances instead of the academic Euclidean distance, and we use service times. So when one truck visits a client, so we take into account that this client has a service time. So we need to add the service time to the cost of the solution. So this is the map of Palma de Mallorca. This is the real placement of the air transit warehouse. We can see here in the upper part of the slide. And what we need to make is when the ship arrives to the port, then all the packages from this ship are delivered to the warehouse. And once these packages arrive at the warehouse, we need to distribute them along the clients. This is the disposition, the geographical location of all the clients of the deliveries of the packages that form the real world instance. There are 44, and I'm going to show now a small video in a platform created by Erhard Serikat, in which how it looks a real route calculated by our solver. We can see here that there are not just straight lines. In this case, there is a real route that goes to real streets and visits all the clients. And just to finish, I want to say that this use case, this research, this algorithm that I have talked about in this presentation is published in Scientific Reports Journal. It's openly accessible, so you can accede through this link, and also that we have another paper with an extension of this research addressing also time windows and simultaneous pickup and delivery. You can check the paper in archive. This paper has been accepted in the International Conference on Quantum Computing and Engineering, which is going to be held in September in Albuquerque, in New Mexico, in the United States. So if any of the audience will go to this conference, we can meet there. We can talk about our research, about this, also about this use case if you want. And that's it. But prior to this, let me check the solutions of the last instance. As you have seen, the last instance that I have computed is already computed. The 4 roots have been already calculated. And again, just to see that we have seen a real demonstration. Again, we can see here that the access use have been increased, and this have been updated with the new execution. So that's all from my side. Thank you so much for the audience, and if you have questions, you can ask, and I will try to answer all the questions that you have.
All right, thank you very much, Nico. We do have lots of questions coming in, so I'll just start from the top. What are the cost benefits of using DWave's quantum annealing computing to the package delivery problem? Is it significant, and do you see this spreading to other companies and industries?
In this case, we have just test this solver with Air Transit with this real world use case. We are now with Air Transit talking about extending this proof of concept with new data, new characteristics, but at this moment, we have just used this use case. The cost benefits, the thing is that when we present these results to Air Transit, they make a very positive evaluation of the solutions. They say to us that the routes computed they are optimal. So the reception of the client, in this case client, it is a proof of concept, okay, but the feeling is that the solutions meet this real client needs.
Okay, does your algorithm improve as the number of priority clients increase? Is there a minimum number of priority clients before your solution no longer works?
No, in this case, there's no minimum number of priority clients, because there another kind of subroute that can be calculated, which goes from one priority delivery to another priority delivery. So you can go merging different kind of priority deliveries, but there's no a minimum. There's no a minimum. The system checks which are the remaining priority deliveries, and depending on the time, the capacity remaining to the track, so it decides which is the next subroute or the next route to be calculated. So in this case, there's no minimum, and the algorithm works as what's in the same way, regardless the number of the priority clients that we have.
Okay. How do you go about choosing between using CQM, BQM, etc.? And you can talk about some of the other work you've done, I know, because you've also used the NL solver, but how do you decide which solver to use for a particular problem?
Yes, the thing is that the BQN is a good solver, but the CQN is more flexible to deal with these very complex constraints. As I talk, I have not talked in this presentation about the mathematical formulation, but you can go to the paper that we have published. Is openly available. There are all the mathematical restrictions that we take into account, and there's some of them, they are very complex, and it is easier to be solved or to be addressed by the CQM hybrid solver. And we have also found at this moment more flexible to use the CQM rather to the non-linear program hybrid solver. It is our next step. Our future work is to solve this same problem with the nonlinear, the new solver of DWave, the nonlinear program library solver. But at this time, we decided to use the CQN because of this reason, because it's very powerful to contemplate very, very complex restrictions.
Okay. Was it a significant effort to use the DWave quantum computing capabilities for your problem?
It is a significant effort to
Was it a
use.
significant effort to use the DWave?
I guess that the most complicated thing, maybe the most challenge when our challenge when we use the D-Wave quantum computing for solving this problem is that we need to form the CQN solver is very, 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 very powerful solver. But the thing is that to use it, you need to formulate your problem in a way that the CQN can solve it. So the main challenge is to formulate your problem in the most efficient way and in a valid way for the CQN to be solved. So this is the greatest challenge. But once you do it, it is quite challenging. The mathematical formulation, if you check the paper, it is not a formulation that you can make in one day. It's a formulation that it takes a long time. It takes a long test, a lot of tests. You need to make a lot of tests with a lot of instances, a lot of situations. What if we have 2 priority clients? What if we have no priority clients? So this is the most challenging part when we work with this, with the D-Wave hybrid solver service algorithms.
Yeah, I will say that that's really the function of our professional services team too, for people that are new to this. Because people working in logistics, manufacturing, they understand their business problem. And we are experts in translating those kinds of problems into what the quantum computer needs. So that's kind of a nice marriage between domain expertise and the technical expertise. But clearly a lot of Nico and others have been to training classes. And once you've done the first problem, it's a whole lot easier to do the second one. Next question, how quickly can a solution adapt or be updated for unforeseen events, changes along the route, like accidents, floodings, etc.? And is this a problem that a real logistics company would tend to run kind of many times during the day?
In this case, the routes are computed when the deliveries arrive at the warehouse. So we don't contemplate these dynamic routes. We don't contemplate accidents or floodings. But for this problem to be solved, we need to introduce the information of the problem to the solver. Again, you can check the paper, and along with the paper, we also share the instances. So how should be the information that you need to introduce to the solver. So the thing is that if the company is aware of an accident once the routes are calculated, so the only thing that the company needs to make is adapt or recompute the input information and then run again the solver with this new information. So in this case, this is something that we have not contemplated, but it is not a real problem because it depends on the information that you introduce outside when you introduce as input to the algorithm.
Okay, we have a number of people kind of asking about the performance of this approach, leveraging quantum capabilities as opposed to using really a kind of classical only method. So I don't know if you compared it in this. I know you've done it in other work, but wanted to get your thoughts on that.
When we okay, this is something that when we send a paper to a journal, the reviewers always say the same. But the thing is that if you check the problem, it could be this one, or it could be the beam packing problem that I have talked in the initial part of this presentation. The thing is that to build or to implement an algorithm that solves this problem or that solves a 3-dimensional beam packing problem with a lot of restrictions, it is itself a research. It is itself a project. So it's a huge effort. So what we make in this case, what we made is to calculate, to check how good is our system calculating the subroutes. And for doing that, we compare the CQN hybrid solver with Google OR tools. And in this case, we demonstrate that our solver is efficient, is very, very efficient. It obtains the same results as Google OR tools, and in sometimes in less time. And also in our other research papers that we have made, that I invite the attendees to go to my Google Scholar profile, and there's some other papers. We compare with other classical solvers such as Gurobi. When we work with, for example, the CQM or the nonlinear hybrid solver of DWave, when we deal with simpler problems, we compare sometimes with Gurobi, and the results are also very positive. Usually, the nonlinear program hybrid solver or the CQN hybrid solver, they obtain a similar performance in terms of the quality of the solution, but in terms of runtime, the quantum hybrid algorithms are much better. And this is something very important. Maybe in some use cases, they are not very important, but in real industrial use cases, the runtime could be very important. So we cannot spend 3 hours to calculate a beam packing solution. We cannot wait 3 hours to calculate a route. We just need to calculate a route in 5-10 seconds. So for this reason, using these algorithms is quite efficient. We have found it very, very efficient.
So there were also a number of questions about the number of locations. So you demonstrated 44. By the way, how many trucks, that was 4 routes that were calculated out of that? Is that correct?
In the instances that we have solved, we have worked with at most 5 different tracks. That remember that each track can deal with different kind of different routes, but they must respect the working hours of the drivers. But in this case, the maximum number of tracks has been 5, and the maximum number of clients is 44. That again, being a quantum-based solver is a lot. 44 is a lot, and the results have been very, very good, very appreciated by Air Transit, and very competitive in terms of performance and in terms of runtime.
And how would you scale this up? So if you went from 44 locations to a logistics company that had hundreds of thousands, how would you approach that kind of a problem, and would quantum help?
Okay, the thing is that we have not solved an instance of a few thousand, so I can talk about the instances that we have solved. And the thing is that when you work with the hybrid solvers that you can find in the hybrid solver service of DWave, one parameter that you can introduce to the solver is the time limit. So you can limit the time that the solver can work. So the thing is that it doesn't matter how much clients that you have. In the real world, this is also important. In the real world, there are, this is the information that we take in from Air Transit, which is a top company here in Spain. In the real world, there is no instance that they have never need to serve 1,000 clients in one day. They need to calculate several routes by day, but the number, because sometimes we talk about the scalability and we talk about what if we solve a 3,000 problem or 3,000 size problem. Okay, this could be very, very interesting, but it is not real, because it could be exceptions, but most of the logistic companies, they don't need to solve a 5,000, 1,000 noded instances or client instances. So in this case, in the real size problems, the scalability is good, but you can control this scalability in time modifying the time limit parameter of the algorithm. So you can more or less define the time that your algorithm will work.
Wonderful. I think with that, we have a lot of questions still remaining, but I think we are out of time at this point. So Nico, thank you so much. If you would just put up the link to the paper again, so people can take a screenshot. We will make the slides available. We will send out a link to the recording. And you can take a look really and kind of dig into the details here at the link that he's showing on the screen. So thank you so much, Nico, and thanks everyone for coming.
Thanks.
And we look forward to seeing you at a future DWave webinar.
Thanks so much.